Good afternoon. I welcome you to the session of experimental methods in fluid mechanics, and today we will discuss about another module of the flow measurements, flow measurement technique, that is the measurement of velocity components by using probes. In fact, in one of my previous lecture we have discussed about the measurement techniques or the measurement principle of velocity and other flow parameters, static pressure, stagnation pressure using probes, and where we have discussed about the 3 hole and 4 hole probes. If we try to recall that we have discussed 3 hole probes are not suitable in places where flow is 3 dimensional, and for that the concept or the new design of 4 hole probe came, and the addition of another hole, that is probe, that is why it is called 4 hole. So, the 4 hole probe, 4 hole probe. So, this 4 hole probe, 4 hole probe is used to measure flow parameters, that is static pressure, stagnation pressure, and also you can measure the velocity components. So, today we will see that using this 4 hole probe how we can measure the velocity components. That is very important in in different areas of fluid mechanics research, in particular where you would like to measure in the axial flow machines or in different other turbo machines. So, now but before I go to discuss about the measurement, rather I can say velocity calculation of velocity components, I would like to redraw the schematic of a 4 hole probe, and from there we will try to understand how we can calculate velocity components using this probe, to be precise by measuring the pressure using this probe. Now, so the schematic of a 4 hole probe, that is very straightforward, that I have drawn it in one of my last lectures. So, this is simple type, and so this is that is this is steel tube which is having 3 different probes. Say this is the central, so this is number 1, this is 2 and this is 3, and another hole is there, that is the 4 hole, and this 4 hole. So, this is 4th number of orifice or hole. Now, we have discussed that these are the radially drilled hole, and these holes are connected through pressure tubing. Now, connected to the pressure tubing. So, this probe is used to, in fact we can place this probe, this is a special type of probe where we can place even we can place this probe in places which is rather which are close to the solid wall, solid boundary. So, again I need to draw another view of this probe. So, if I try to draw, say this is, in fact I can draw the here only. So, this is the central hole, and so this is So, this angle is 45 degree, this angle is also 45 degree, and this is number 2, this is number 3, this is number 1 and this is number 4. Now, if we try to recall, this hole is suitable for measurement of flow parameter, that is static pressure, stagnation pressure, and as well as the velocity components, and this is suitable in places where flow field is highly 3 dimensional, and also this probe can be placed very in a region which is close to the solid wall or solid boundary. Now, what is done essentially, that is we will discuss today. See, this probe, this as I said that there are 3 different 4 different holes. Number, yes, that is central hole 1, then hole 2 and 3, these are connected. Now, we need to know that these probes, that is holes, multi holes or probes, these are connected to the pressure pressure tubing. Now, that means using this probe we can measure the pressure, and once we calculate pressure, then from there we can calculate the velocity components, and that is what we will discuss today. Now, how can we measure pressure using the probe, that is now we will discuss. We have discussed that this probes 2 and 3, this probe 2 and 3, these are connected with, rather I can say that the pressure tubings, or I can say pressure leads. Now, the pressure leads are these pressure leads are connected to projection manometer and one U-tube manometer. Now, these point probes 2 and probes 3, these 2 probes are connected to U-tube manometer. U-tube yaw balancing manometer, to be precisely. So, there are 4 different probes. The probes 2 and 3, these 2 are connected to U-tube yaw balancing manometer, and other 2 probes are connected to the projection manometer, right. So, that is what we have understood. So, which probe is used to measure static pressure or stagnation pressure, that we need to know. That means, which probe is used to measure which pressure, that is we should know, but now I can see that we will get pressure P1 using the probe 1, we will get pressure P4 using probe 4. 2 and 3, these 2 probes are connected with U-tube yaw balancing manometer. So, these 2 probes are responsible. We will discuss why these 2 probes are connected with yaw balancing manometer. So, I can say that our reference pitot probe is used to measure the total pressure, right, that is PT, and static pressure PS in the jet is equal to the atmospheric pressure. So, I am placing this probe in a jet where the jet static pressure is equal to the atmospheric pressure Ps, a reference pitot probe which is used to measure the total pressure. Now the probe is eared. Now why it is done? I have discussed this aspect while we have discussed about the working principle of the probe. Now probe is eared until pressure at point 2 and 3 becomes equal. So pressure at orifices 2 and 3 must be same. For that the probe needs to be eared, and this process is done until the pressure at orifices 2 and 3 becomes equal. And if the pressure becomes equal, the the balancing manometer will show the zero differential head. So that means I can write now that the probe is eared until pressure at orifices 2 and 3 becomes equal, and how do I know that the pressure is equal? If the pressure is equal, then balancing manometer, rather pressure, if the pressure becomes equal, the balancing manometer will show zero differential head. Balancing manometer will show zero differential head. So knowing the reading from the differential manometer, we can say now the pressure at point 2 and 3 is equal. So that is done until by earing the probe, and until it is done until they become equal. The yaw angle at which the pressure or the yaw angle for which the pressure at orifices 2 and 3 becomes equal, that yaw angle is known as the reference angle of the probe. So the yaw angle for which, or I can say the yaw angle reading at this position gives the reference angle of the probe. So what I said, the probe is eared until the pressure at orifices 2 and 3 becomes equal, and when they become equal, we will come to know from the reading of the balancing manometer. The balancing manometer will show zero differential head, and at that position the yaw angle if we know, and that is the reference angle of the probe. So that is the case. Now what is done? Manipulating the pressure taps, the value of P1 minus P2. So now what we will do, if I go back to the previous slide. So 2 and 3 are connected to the yaw balancing manometer. Probe is placed in a jet, and we can calculate the total pressure using a reference pitot probe, right. 2 and 3, since they are connected to the yaw balancing manometer, the probe will be yawed until the the differential the differential head on of the yaw balancing manometer is 0, and at that position we will read the yaw angle, and that is the reference angle of the probe. Now what I can calculate now? I can calculate the P1 minus P2, that manipulating the pressure tap, and of course P1 minus P4. So and P1 and PT. So what I can do now? Now by manipulating the pressure taps, the values of P1 minus P2, since P2 and P3 are equal, that is what. So P1 minus P2 is as good as P1 minus P3, P1 minus P2, P1 minus P4, P1 and PT, that is the total pressure that is obtained using a reference pitot tube. So these are read out from the manometer, right. So this is and what this process, I mean, so what we are doing, we are placing the probe in a jet, we are using a reference pitot probe to calculate the total pressure. The atmospheric pressure of the jet static pressure is equal to the atmospheric pressure. The probe will be yawed until the pressure at orifices 2 and 3 becomes equal. That will come to know from the differential head, from the zero differential head of the yaw balancing manometer. Once the pressure at orifices 2 and 3 becomes equal, then we will read the yaw angle measurement, yaw angle, and that is the reference angle of the probe, and at that position by manipulating the pressure tap we will calculate the P1 minus P2, that is what we have written, P1 minus P2, P1 minus P4. Since P2 and P3 are equal, so P1 minus P2 is as good as P1 minus P3, and P1 and P2. So we will read this reading, we will read this from the manometer. Now the procedure is repeated for different pitch angle with a in step of 5 degree and in the range of plus minus 45 degree. So each time pressures are read only when pressure, again I am telling. So we will calculate P1 minus P2, P1 minus P4, P1 and P2. So the procedure is repeated in steps of 5 degree, and it is and in the range of plus minus 45 degree, and each time we will read, rather we will take readings when pressure at orifices 2 and 3 becomes equal. So now question is, after knowing P1, PT, P1 minus P2 and P1 minus P4 from the manometers, as I said, P1 and P2, this I mean 1 and 4, these two orifices are connected to the projection manometer, 2 and 3, these two orifices are connected to with U-tube manometer, that is balancing a manometer. Now taking reading from this reading of the pressure from this manometer, now we can calculate a few coefficient, that is the pitch coefficient and the total pressure coefficient. So now what I will do, this calibration, that is known as calibration. So the calibration results are presented in terms of the probe coefficient. So the calibration results are presented in terms of probe coefficient, right. And so what I said, the as I said that process or procedure is repeated in steps of 5 degree and in the range of plus minus 45 degree, right. So and that is very important, that each time the pressures are measured when pressure at EO orifices, that is orifices 2 and 3, is balanced. So, that means this is the procedure. I do repeat again. So, what are the steps? We need to place the probe in a jet. Our reference pitot tube is our reference probe is used to measure the total pressure. Now, that is what I have written, that our reference pitot probe is used to measure the total pressure. Static pressure of the jet is equal to the atmospheric pressure. Now, the 1, 2, 3 and 4, there are 4 different probes. 1 and 4, these 2 probes are connected to the projection manometer. Probes 2 and 3 are connected to one U tube EO balancing manometer, and these orifices are known as EO orifices. What is done? After placing the probe in a jet, the probe is EO'd until the pressure at orifices 2 and 3 become equal. When the pressure at orifices 2 and 3 is equal, we just take the reading of the EO angle, and that is the reference probe angle or reference angle of the probe. And when the differential head is 0 of the differential head of the EO balancing manometer is 0, then we will come to know that the pressure at orifices 2 and 3 is equal, and at that time we will calculate by manipulating the pressure tabs, that is P1 minus P2, P1 minus P4, P1 and PT. Now, this procedure is repeated in steps of 5 degree and within the range of plus minus 45 degree. One thing we need to note that each time of the calibration, we need to measure pressure from the manometer when only the pressure at orifices 2 and 3, that is at EO orifices, is balanced. So, now this calibration results can be presented in terms of the probe coefficient. So, that means we can define a few probe coefficient, and which we will write now. So, that is the pitch coefficient, that is Cp, and this is P1 minus P4 divided by P1 minus P2, total pressure coefficient equal to Pt minus P1 divided by P1 minus P2, and static pressure coefficient, that is P1 minus Ps divided by P1 minus P2. So, these 3 coefficients, these 3 different coefficients are calculated, rather calibration results are presented in terms of this pressure coefficient. Now, we should know, rather we need to know, knowing this pressure coefficient, how can we calculate the velocity component? That is another important thing, and we should know, because using probe we can measure the pressure and we can represent those pressure in terms of the different coefficient. And so, now I will try to explain how I can measure the velocity components. See, we know that if we place the probe in the jet, so say the dynamic pressure, just I am doing this mathematical calculation. So, dynamic pressure we know half rho into c square, if c is the absolute velocity of the jet. So, c is the absolute velocity. Now, this is nothing but Pt minus Ps. So, this is total pressure minus static pressure. And So, we can write this half rho c square is equal to Pt minus P1 divided by P1 minus P2 plus Ps or P1 minus Ps divided by P1 minus P2 into P1 minus P2. So, this algebraic manipulation we are doing essentially to express this dynamic pressure in terms of different pressure coefficient that we have defined in the previous slide. So, what I can write, therefore, this C okay, half rho c square, or I can write c square will be equal to, so this is we have defined Pt minus P1. If I go to the previous slide, Pt minus P1 divided by P1 minus P2, and that is what is defined by total pressure coefficient Ct, and this is static pressure coefficient Cs. So, now I can write this is Ct and this is Cs. So, I can write 2 Ct plus Cs into P1 minus P2 divided by rho. So, that is we can write c square is equal to, of course, so 2g I can write rho g. Now, I can write one step further, that is c is equal to twice g into Ct plus Cs into P1 minus P2 divided by rho into g power half, right. So, this P1 by rho g and P2 by rho g. So, these two terms are there, I can rather we can see from this expression. So, this P1 by rho g, that is pressure at orifice 1 in meters of head, and P2 by g, that is pressure at orifice 2 in meters of head of the flow. When P2 is equal to P3, that is very important. Head in meters of head of the flow. So, that is this P1 by rho g, that can be written the expression C, that absolute velocity can be written in terms of P1 by rho g by and P2 by rho g. So, P1 by rho g, that is the pressure at orifice 1 in meters of head of the flow when pressure P2 and P3 are equal, that is P2 is equal to P3. So, now, so what we can do, that means we have calculated the total pressure, I mean total absolute velocity. So, if I now draw the schematic, then from that schematic it will be clear, knowing see how I can calculate the component of velocity. Say this is the probe axis. So, this is the probe axis. Say this is probe axis, and say this is normal to the probe. Normal to the probe, and say the component of velocity, that is C, this is C. So, this is C, absolute velocity. So, this is C, and this makes an angle beta, and this beta is known as the pitch angle. So, beta is the pitch angle. So, that is if I try to recall, rather if we try to recall that the pitch characteristics of the flow, to know or to measure the pitch characteristics of the flow, we have modification of the 3-hole probe, that means the concept of 4-hole probe came into the picture. So, the pitch characteristics of the flow cannot be measured using a 3-hole probe. So, to measure the pitch characteristics, additional hole is there, and the responsibility of additional hole is to obtain the pitch characteristics. So, this is absolute velocity c beta. Now, this component, so this is beta. Now, this component is c sin beta, and this component is c cos beta, right. So, this is the front view. Now, if we take the top view, the top view will be like this. So, this is c cos beta. So, therefore, this will be, and this angle is phi, and phi is yaw angle. So, this will be c cos beta cos beta sin phi, and this component will be c cos beta cos phi. So, the c cos beta cos phi is c n, and c cos beta sin phi is equal to c t. So, this is the tangential component of the absolute velocity, and this is the normal component of the absolute velocity, c n and c t. So, that means this is the top view. So, now say I can tell that say this is pump axis. This probe is used to measure the static pressure, stagnation pressure, as well as the velocity component for a centrifugal pump. So, I mean, we are placing the probe to measure the static pressure, stagnation pressure, and the velocity components. The static and stagnation pressure, that is, we have seen that is obtained using the probe coefficient, total pressure coefficient, stagnation pressure coefficient, and the static pressure coefficient. Now, so this is pump axis or reference direction, or this is reference direction, right. I can say this is horizontal axis, and if I try to recall that say velocity component, that is c cos beta, and this angle is phi, and so this angle and this angle is 45 degree, and I can draw like this. So this is the, so C cos beta is normal to the probe axis, but it has a yaw angle phi. So this is I mean it would be much more clear. That means if I, so C cos beta which is normal to the probe axis, but it has a yaw angle phi. So that means I mean I can draw the I can draw another one schematic from there, it will be much more clear. So say this is say this is C and this is C cos beta, right. This angle is beta and this is C sin beta, and the C cos beta which makes an angle phi. So this angle is phi. So this angle is phi. So the C cos beta which is normal to the probe axis, C cos beta which is normal to the probe axis, but it has a yaw angle phi, and that yaw angle, as I said you, that it is yawed until the pressure at the orifices 2 and 3 becomes equal. So now, so today what we have discussed, from this schematic it is clear that if we place a probe in a flow field in a jet, and if the absolute velocity of the jet is c, so using this probe, as I said that using this probe we can measure following the steps that we have discussed today, we can measure pressures, that is total pressure, stagnation pressure. Also the measured results are presented in terms of the calibration coefficient. So pressure at orifices 2 and 3 they are equal, pressure the orifices 1 and 4, these two orifices are connected to the projection manometer. So we can calculate P1 and P4 if we know P2 and P3, because that is the procedure we need to follow. From there we can calculate P1 minus P4 and P1 minus P2, and the static pressure of the jet is equal to the atmospheric pressure, and the total pressure is measured using a reference pitot probe. So knowing all these pressures, we can represent result in terms of the pressure coefficient. Now if the dynamic absolute velocity is c, then the dynamic pressure half rho c square can be represented, that is total pressure minus static pressure, and doing this through this mathematical analysis we have seen that the c square, the velocity component, the velocity can be represented by this form, where P1 by rho g and P2 by rho g, these two are the pressure at orifices in meters of the head of the flow, and P2 and P3 will be equal. Now if the c is the absolute velocity, and this two different that is front view and top view, we have shown the velocity components. From there it is clear that if the c is the velocity of the jet and it has a component c cos beta which is normal to the probe, but this is also has the C cos beta has another component, that is but with an the C cos beta makes an C cos beta has a Young angle phi. So, C cos beta can be decomposed further two components, that is C cos beta sin phi and C cos beta cos phi. The C cos beta cos phi, that is the normal component, and C cos beta sin phi is the tangential component of the velocity. So, knowing the jet which is in a within the turbomachines in the centrifugal pump, by placing the probe we can calculate the velocity components. So, if we know the velocity components, from there we also can calculate the what will be the flow rate, and if we calculate the flow rate and by knowing the velocity components, and if we theoretically measure the flow rate from the pump, we can check whether our calibration results are correct or not. That means, by knowing the measurements of different pressure, we can calculate the different velocity components following the steps which we have discussed today, and knowing the velocity components we can calculate flow rate. Now, the mathematical calculation of the flow rate, once we know the velocity components, will be compared with the flow rate delivered by the pump, and if we find a closer match, then we can say the calibration results are correct. So, this probe are important instruments, rather I can say the multi-hole probes are important instrument to measure the static pressure, stagnation pressure, as well as the velocity components in places where velocity field is highly three dimensional, and which is also very close to the solid boundary. So, to summarize today's discussion, we have discussed about the operational principle of the multi-hole probes in one of my previous lectures, but today we have discussed about the procedure by how we can calculate the velocity components by measuring the pressure using multi-hole probes, and knowing the velocity component we can check whether the velocity component measured velocity components using this probe is correct or not, and for that we can calculate the flow rate, and that flow rate will be compared with the actual flow rate that is delivered by the pump. So, with this I stop my discussion today, and we will continue our discussion in the next class. Thank you.